Bun găsit la emisiunea Știință și Cunoaștere. Astăzi continuăm difuzarea părții a doua a interviului cu profesorul de Geografie și Climatologie Tim Ball din Canada. Așa după cum probabil bănuiți, ceea ce ne spune domnia sa nu prea este în acord cu directivele de politici climatice stabilite în cadrul diverselor întâlniri la nivel înalt organizate de Panelul Interguvernamental pentru Schimbări Climatice. Tim Ball este un personaj destul de controversat și l-am rugat să-mi explice câteva dintre problemele cu care s-a confruntat. Una din ele se referă la două pagini de Wikipedia în care autorii acestora îi prezintă pregătirea academică în două versiuni diferite. Pe una din ele, Tim Ball este menționat ca fiind profesor de geografie în perioada anilor 1988-1996 la Universitatea Winnipeg, iar pe o altă pagină este trecut ca fiind profesor de climatologie la aceeași universitate. Am aflat că domnia sa a predat la Departamentul de Geografie al Universității, dar are un doctorat în climatologie, după cum se va putea vedea din imaginile extrase din CV-ul său personal. Din modul foarte echilibrat, argumentat și documentat în care mi-a prezentat până acum știința mediului, sunt suficient de convins că pregătirea sa reflectă în mod real cunoștințele în domeniul climatologiei și nu doar a geografiei. Am considerat că este necesar să vă atrag atenția asupra acestor detalii, deoarece unii dintre reprezentanții României în panelul interguvernamental pentru schimbări climatice ar putea să conteste pregătirea profesională a invitatului meu. Trecerea timpului în cele din urmă va confirma sau infirma declarațiile sale. Nu mai e mult până când vom începe să observăm semnele unei schimbări climatice, dacă nu cumva acestea deja se și produc. În minutele următoare, Tim Ball ne va prezenta influența solurilor și a elementelor topografice asupra climei, va vorbi despre rolul circulației curenților atmosferici, rolul norilor în reglarea termică, iar spre final veți afla adevăratele cauze ale intensificării nivelurilor de radiații cosmice și solare, care ajung la altitudini din ce în ce mai joase. Dear Professor Tim Ball, welcome back to our Science and Knowledge TV program in Romania for part 2 of our interview.
Well, thank you, and I appreciate the opportunity to try and help people understand what's going on with the weather and climate.
I have a question somehow off topic, but there are 2 or more pages of Wikipedia with your name, and in one of them they said you were a professor of climatology. In another one, they said you were a professor of geography, but at that time, the University of Winnipeg did not have a climatology department. Can you clarify? I don't see anything wrong for a geography professor to talk about climate and Earth, because geography should include most of the basic elements regarding climate changes.
Yes, what's going on, of course, is because I have and people in Romania will be familiar with Copernicus and Galileo and all these people in science who dared to question what the prevailing wisdom was. You become a target. And there's a professor at Oxford University by the name of William Connolly, who was part of the whole political use of weather and climate and global warming for a political agenda. He happens to be a left-wing professor, and of course they think that industry is wrong, and that capitalism is wrong, and that we need communist governments and so on. And people in your country know all about that. Like Václav Klaus said, we've gone through 70 years of communism. Why would you want to go back to that? But Connolly controlled over 500 Wikipedia entries. He was the editor. And Wikipedia, you can go in and change entries in Wikipedia yourself, but you can only make 3 changes, and that's it. The editor can change as often as he or she wants. And so Connolly was putting entries into Wikipedia not only about the climate and the weather, but also about the people like myself that were challenging what they were saying. And you go in and correct it, and within 20 minutes, he changes it back to what it was. They finally fired him as an editor of Wikipedia, but somebody else took over what he was doing. Wikipedia, a great deal of what is on there simply cannot be believed because people with their agenda put on what they want to be put on there. So what you read on Wikipedia about me is information that was created by a public relations company, a guy who's the chairman of an environmental group here in Canada.
But why there are two pages? In one of them they said you were a professor of climatology, and in the other that you were a professor of geography.
Okay, well, because what happened was after they fired Connolly or took him away from being the editor, somebody else put another entry on there about me saying, no, here's a different story. So that's why you've got two completely different stories. Neither one of them is completely correct. That's the problem. And if people want to read about my career and past, they can read my own website where I explain it all. Now, the question, your question about you didn't have any problem with a geography professor studying climatology is because geography is the original generalist integrative discipline. That is, geographers are trying to look at the map, make sense out of the whole picture, which is what I talked about earlier when I talked about the picture puzzle. What we talked about, I think, on one of the earlier programs was the change from generalizing to specializing. And the amount of information has become so great that for one person to grasp everything that was going on is not possible. So it's generally conceded that the last, what we call universal person, that is, he knew all of the science at the time, all the chemistry, all the biology, all the physics, was a fellow by the name of Alexander von Humboldt, a German who traveled to every continent, in fact, drew the first weather map. And he died in 1859. That's the same year that Darwin's Origin of Species was published. And of course, that changed science in that it said, look, we need evidence, we need data, we need information. And the amount of information grew so that no one person could handle it. So now the climate scientists are people that only have one piece of the climate puzzle. I'm trying to put the whole thing together. Climatology was always taught in departments of geography. That's why I was in a department of geography. And there was, in fact, a separate climatology department at the University of Winnipeg. It was on a separate floor from the geography department. So that information is simply false.
But you are teaching at the Department of Geography?
Yes, because that was where my degree in climatology was done, in the Department of Geography at Queen Mary College at the University of London. Because climatology generally has always been taught in departments of geography. Just the same with geomorphology, which is study of the surface of the land, and they were generalist disciplines. But once computer models came in and you got getting specialists and people who only studied CO2 or only studied ocean currents or only studied one part of the puzzle, they started to dominate. And of course, what's happened in our society is, and say Western society, that to generalize is considered the mark of a fool, to specialize is the mark of a genius. But the problem is, you might know a great deal about one small thing, but if you can't explain how it fits into the larger puzzle, it's a waste of time. So, of course, and particularly the people that are the computer modelers, they think they know everything. But all they are is computer modelers, and their work is only as good as how they built their computer model.
Okay, but just in few words to clarify. You are teaching at the Department of Geography, but your PhD is in climatology.
Yes,
okay,
yes.
Okay.
Yeah, and I can send you a copy of that if you want to put it on your website. It's available on my website, the actual document showing that I have a PhD in.
Okay, yes. My next question is related to the land. how does the different types of soils and topographic elements influence the climate?
When we're talking about climatology, it's done on different regions and scales. So if you're studying global climate, you're studying the whole global climate, the atmosphere and everything else. As you get down, you can study microclimates. So the climate, for example, people study the climate around a particular plant. Or you can have regional climates, like the climate of a city, which is just different from the countryside. So urban and rural climates are different. And so when you're studying at those levels, then when you're doing global climate, it's just the surface. But when you're studying the local climate, it's what is the soil? What is it made up of? How does it absorb water and evaporate water? How quickly do some soils heat up quicker than others? And so the nature of the surface is absolutely critical. And one analogy I can give you is that the surface of the earth, whether it's water or land, it's like your skin. A lot of people don't know the skin is probably one of the most important organs of the body. And because it is what we call an interface. It's a boundary between two completely different elements. So you've got the atmosphere and the land, the soil or the rock or the oceans. And what happens across those boundaries determines what sort of local weather you're going to get. For example, if you've got a field that has no grass on it, the farmers plowed it and kept the weeds and grass off of it, the snow on it will melt quicker in the spring than where you've got grass and the snow remains. And I remember flying over Canada where we've got this square system of fields called sections, and it was almost like a chessboard where the fields that had been kept black with just soil, the snow had melted. The other fields that had the grass or on them were white, so it was like a checkerboard. And the color is also a factor. So a dark surface will absorb more sunlight than a light surface, which is why, of course, you see with solar reflectors, they're a matte black because that absorbs more of the sunlight. If you've got a white surface, so let's say that you've got a black soil, it will absorb about 85% of the sunlight, which then means that surface is going to heat up more. If you've got a snow surface, then it only absorbs about 5% of the heat from the sun. 95% is reflected back out to space. That color of the surface is called the albedo. So when you go out in space and you look back at the Earth, and one of the things that surprised the astronauts looking at the Earth from the moon was how bright the Earth was, because about 35% of the sunlight that reaches the Earth is reflected right back out to space. That's called Earthshine. People are more familiar with moonshine, okay, because you look at the moon and it can be very bright, and yet it's only reflecting 7% of the sunlight that hits it. So it gives you an idea of how the color and the texture of the surface absorbs the heat energy. But with soil, of course, it's also in terms of its ability to hold moisture, rates of evaporation, and so on. So the surface is very important. The other thing is the topography. So, for example, if you look at a mountain range, you will see glaciers on the polar side, but on the tropical side, the south side in the northern hemisphere, the snow and the glaciers are melted. All right, because the angle of the sun and the shadow will affect, and you can get that even in a field. You just get a small rise. One side will have a different climate than another side. And you can also see that, for example, in many areas, we've got areas in Canada where a south-facing slope won't have any vegetation on it, trees. The north slope will have trees. The reason is because the south slope, the heat from the sun evaporates the moisture, so there's not enough moisture for only grasses to grow. But on the north side, the evaporation loss is much less, so trees can be supported. So the angle and the direction of the slope will affect the climate considerably. And of course, people know that in their gardens and in their houses. People want houses with, a south-facing because of the sunlight, or you want your garden with access to sunlight and so on. And so the topography has a huge influence on the local climate.
Romania is the only country who has almost all kinds of topographic elements and soils, at least in Europe, if not more.
Yeah, microclimates. And you can even, and it's interesting, if you ever ride a motorcycle in the summertime, you suddenly become aware of how much the temperature is changing because of whether it's a dark land around or light land. Amazing the variation in temperature and precipitation. And you remember I talked about that rainfall earlier with the showers and thunder showers. Farmers will know that their neighbor could get good rain. They don't get any rain because the rainfall pattern is affected by the topography and the climate. And it also, by the way, it directs the weather. We had a tornado here in Edmonton in Canada a few years ago. And the tornado, of course, is a huge power and spinning very fast, but it actually followed, it was very flat terrain. The tornado actually went along a creek bed because it was directed by the topography. So yeah, the topography, and I would agree with you about Romania, by the way, because of course Romania is on that boundary between the area that was glaciated and the area that wasn't. You've got tremendously variable soil, some very, very good soil areas and some very poor soil areas, and that will have tremendous difference on the climate conditions.
Please tell us about the atmospheric circulation and how does the winds really works?
Okay, wind is probably the one huge variable that is ignored in the climate models and in studying weather. For example, you can have a very hot, dry time, and you'll have certain loss and effect what we do. But if the wind blows, it's far worse, because the wind takes the moisture away. But wind is created where you've got difference in pressure, and difference in pressure is created by difference in temperature. So you've got a cold area and a warm area. The warm area will heat up more, the surface. That air will start to rise, okay? That creates a low pressure. The cold area is high pressure. Nature will try to equalize that pressure in that the air will then move from the high pressure to fill in the low pressure. That movement of air from the high pressure to the low pressure is wind. That's all it is when we talk about the air rising because of the heat, just like you see it going out of a chimney, that's convection. That's a vertical rise. That also is a wind. But we don't think about it as a wind. Vertical winds are very important in the atmosphere. Horizontal movement of air, we call wind, but scientifically it's advection. Okay, so you got advection and convection. Of course, within the atmosphere, if you've got wind blowing here, rising here, then it moves across at the top, and you get a complete circulation cell called a convection cell. And the most significant of those on the planet is the Hadley cell. Now, George Hadley was actually a lawyer who was interested in meteorology, and he was getting all these reports about winds from the British Navy. And he started plotting them, and he realized that on the surface of the Earth, the winds were blowing towards the equator. all right? And then they were rising. And so he created this Hadley cell, which is at the equator. You've got air rising. That takes, of course, you've got lots of moisture evaporating. That creates very heavy clouds, heavy rain in the tropics. The air reaches the top of the atmosphere, spreads out. Now, because the moisture's been taken out of it, it's dry and cold. And then as it comes down, it's heated because it's compressed. As the air moves down, the compression creates heat. So by the time it reaches the surface of the Earth, it's very hot and very dry. So when you look at the pattern of global climates, the equator, very hot, very wet. But immediately alongside of it, between 15 and 30 degrees of latitude on average, you have the deserts of the world. So if you look at Africa, for example, Central Africa, the Congo, some of the highest rainfalls in the world, but on each side of it, the Sahara Desert and the Nami of Kalahari deserts, the greatest deserts of the world. And that's because of that circulation of winds created by different pressures. And by the way, one of the problems they had in history when they were trying to sail across through the tropics, where the air was coming down, the sail didn't work, because the sail works if the wind is going this way. If the wind is coming down, the sail doesn't work. So they would sit there, couldn't go anywhere. They had no power. And when the Spanish were going to South America, they would get into these areas, and they called them the horse latitudes. Why did they call them that? Well, because they had horses on board. They didn't have enough feed for them, didn't have enough water for them, and so they had to throw them overboard because they were dying. So that zone, around 30 degrees, became known as the horse latitudes. At the equator, you've got the opposite. Now the wind is going up your sail, right? Not down here. So they became the doldrums. Now the word doldrums, of course, today it means if you're in the doldrums, it means you're just listless and very down. Well, the same thing. Your sail didn't work, but it was because these vertical up and down wind currents are very important. When you look at the globe in total, so you've got hot at the equator, so you have low pressure at the equator, cold at the polar regions, so you got high pressure, that the air then blows from the high to the cold. So if the Earth wasn't spinning, you would have simply winds blowing from the polar regions to the equator, and you'd have what they call a single cell of circulation. So instead of the small cell at the equator that Hadley drew, you have this one large circulation. But because the Earth is spinning, that affects the movement of anything across the surface of the Earth. And it's called the Coriolis effect. And this is something that students had a very hard time understanding. But if you were looking at something from space and it started to move across the surface of the Earth, it would appear to veer to the right. So when the wind starts to blow across the surface underneath is moving. So the pattern that's drawn is for the wind. So when a wind starts to blow in the northern hemisphere, it's deflected to the right. Okay? In the southern hemisphere, it's deflected to the left. So when you've got a low pressure system, the circulation around it is either clockwise or counterclockwise, depending on which hemisphere you're in. Now, one of the things that happens is Coriolis force is zero at the equator. And as you go towards the pole, the Coriolis force increases. You will never have a hurricane form within 8 degrees of the equator because the low pressure forms, but there's nothing to make the air circulate around it. It's only when the low pressure extends out beyond 8 degrees that the hurricane starts to form, because now the Coriolis force is having an effect. So the wind patterns are a combination of high and low pressure regions created by the sunlight, and then the circulation, the spinning of the globe that affects it. And by the way, that Coriolis effect is very interesting. Railways, people don't know this, but when you've got railways, they have to allow for the fact that in the northern hemisphere, the right track is going to wear out quicker than the left track, because the train is constantly being pushed by Coriolis force to the right. It has that much effect. And of course, there's always that story that you like to tell students that if you have a dish full of water with a drain in the center, at the equator, there's no Coriolis or spinning effect, so the water would go straight out through the drain. But in the northern hemisphere, it circulates around because of the effects of Coriolis force. And it's something they have to take into account with when they're launching rockets into space. The Earth is going to spin underneath it. Even if you're firing long-range missiles, you have to calculate that into, by the time you fire the missile to the time it lands, how much is the Earth going to move? So you have to allow for that effect. Well, that affects the winds on the Earth. The basic rule, and this is useful for people, particularly farmers who are watching the weather, in the northern hemisphere, with your back to the wind, in other words, the wind is blowing in your back, the low pressure is on your left. So you can track the movement of the low pressure, and if you're watching it and it's affecting your weather and your rain and so on, you can follow that pressure. And by the way, changes in atmospheric pressure, the old barometer, is still the best instrument for weather forecasting on a 24-hour basis. And you know, the old barometer, and it just can change. But atmospheric change of pressure is still the most important thing. So the winds, of course, are important, not only in terms of moving heat, but in the rate of evaporation.
Yes, this is exactly what my next question is about. Please tell us about the role of the clouds and how can they regulate the climate.
Yeah, the clouds are very, very important. But just to get back to the evaporation idea, if you have no movement of air, and you've got the air over the surface of the water at a certain temperature, there's always molecules of water escaping. So between the surface of the water and the air, there are molecules, water vapor going in and water vapor going out. There's also other gas. CO2 is also going in and out. So remember we talked about the skin. Well, your skin is absorbing and releasing things all the time. It's an interchange. And evaporation rates are controlled by the temperature of the water, because as the water temperature increases, the water molecules' speed of movement, called the Brownian movement, that increases. Temperature is an increase in the speed of the molecular movement. So, for example, people say, well, I felt the heat of the sun. No, you didn't. What you felt was the sun was causing the molecules of your skin to move more rapidly, which you feel as heat. You can achieve the same heat feeling by friction, right? Because you're causing the molecules then to move more rapidly. To escape the surface, a molecule has to achieve a certain speed. It's the same thing as when they're launching rockets into space. To overcome gravity, you have to achieve a speed of 17,000 miles an hour to get out into space, okay? Well, the same is true of the molecules in the surface of the water. They have to achieve a certain speed to escape. So as the water temperature goes up, more and more of them will escape. That is evaporation. The amount that the air can hold is determined by the amount of water vapor that's already in the air. The air's ability to hold water vapor molecules is determined by its temperature. Because if the air is hotter, the space between the molecules is greater, therefore more air can enter, more water vapor can enter, I should say. It can absorb. So higher water temperature and higher air temperatures increase the rate of evaporation. The wind can change all of that, because what if the air becomes saturated over the surface? So the amount of molecules escaping from the surface equals the amount of molecules going in, then there's no evaporation occurring. It's zero. But if the wind comes along and removes that saturated air, now more molecules can escape. That's why a hairdryer works, because you're heating the air, removing or increasing the rate at which the molecules can escape from your hair, the water molecules can escape, and so you've got a combination of the heat and the wind. So that whole evaporation rate is very sensitive. It doesn't take much change in temperature for it to alter. For example, when I was chasing Soviet submarines around the North Atlantic, they used to be able to, we used to have to go and look for Russian trawlers that were fishing off Canadian waters, but they were also monitoring our electronic intelligence trawlers as well. And we would go out what we call passive. We didn't have radar, but we still had to find these trawlers. It was easy when there was fog, because off the east coast of Canada, you get more fog days per year than anywhere else on the planet, because you've got the warm waters of the Gulf Stream meeting the cold air of the Arctic. Therefore, you get the fog forming. And you know that in Romania, the fog forming in the morning. Well, what we found was that the heat exhaust from the engine of the trawler burned off the fog. It added enough heat to the atmosphere to actually cause the fog to dissipate for as much as 20 kilometers behind the ship. That's how sensitive the balance between water vapor and evaporation and condensation is in the atmosphere. It's a very sensitive thing. And you know, in Romania, you'll start the morning with fog, because the ground is cooled. The layer of air near the ground is cooled below its dew point temperature. Condensation occurs, and you now have fog. Fog is actually just a cloud formed at the ground level, right? The water vapor is condensed into water droplets. Water droplets are what you see when you see a cloud. Water droplets are so small that it takes 1 million of them to get together to form a single raindrop. Okay, but when you get billions of them in a cloud, then they become visible to you. Now, what happens when you get fog in the morning, the forecaster will say, well, the fog will clear off by lunchtime, because now the sunlight penetrates, heats the surface underneath, and evaporates the fog. The term they use is it burns off the fog. Okay, so that formation of water vapor condensing into water droplets is very important in cloud formation, because you need a particle, a very small particle, and most of them in the atmosphere are salt particles from the ocean or clay particles from the soil. And clay comes in 3 different sizes. The smallest size of clay is called kaolinite. It's very fine, and it of course is used to make the best china, because it holds 18 times its own weight in water, and therefore it makes very, very fine, strong china. And those particles in the atmosphere are called condensation nuclei. You have to have them for condensation to occur. So you can have evaporation occurring, and you've got water vapor, which is water in its gaseous form. It will stay in its gaseous form unless these little condensation nuclei are present. So in the laboratory, for example, you can create a condition where the relative humidity is 700%, but there's no condensation occurring because there are no nuclei. The minute you put the nuclei in, bing, instant condensation. Okay, that, by the way, is why cloud seeding works, because you've got water vapor, that is, water is a gas in the atmosphere, but there are not enough nuclei for it to form into a water droplet to create the cloud, to create the rain. So you spray silver iodide or dry ice on it, and that's called cloud seeding. What you're adding is more of these nuclei to make the cloud form. Okay. Now, one of the problems, and by the way, of all the clouds that form on the Earth, you only get precipitation out of about 1%. So for rainfall to occur is actually a very complex process. So you'd have day after day after day of clouds forming, but there's never quite enough for a raindrop to form, because you've got to take those water droplets, which, as I said, take 1 million to form a raindrop. You got to get them together somehow. You've got to make them coalesce into a raindrop, which is large enough then for gravity to pull it to the ground as rain. Now, the smallest raindrop you get is called drizzle, and that's like millimeters in size. The largest raindrop is controlled by the surface tension of the water. So if the raindrop gets too big, it breaks into smaller raindrops. It can't hold itself together. And so for clouds to form is a very complex process, and then for rain to form out of that is even more complex. The clouds, of course, are very important in global climate because they are like putting a screen up in the greenhouse. You're blocking the sunlight coming in. And so one of the arguments that was made was they said, oh, if global temperature goes up because of CO2, then more water vapor will be put in the atmosphere because of more evaporation. And water vapor is a greenhouse gas, therefore the temperature will keep going up. Well, that sounds nice in theory, but doesn't work in practice, because what happens is that the cloud forms and blocks the sunlight, right? So instead of a positive feedback of increasing the temperature, you actually get a negative feedback. Now, one of the things that, and we'll get into this, your next topic about cosmic rays, I know you want to talk about that.
Yes, yeah.
Yeah, okay. For a long time, and I would say up until about 1990, we knew that there weren't enough condensation nuclei to explain or account for all of the clouds that were forming. Right? We thought it was the clay particles. We thought it was the salt particles. And one of the things, by the way...
And including also some green algae from the oceans, because Bill Hamilton discovered the wet thermoregulator mechanism used by the oceans and algae. When the wave sparks, the bubble lifts the algae in the air of the few centimeters above the surface of the water, and then stronger vertical currents lift them up until the level of the clouds. And the algae too are playing the role of the condensation nuclei.
Yeah, it's amazing how much salt there is in the air. Obviously not much in Romania because you're a long way from the oceans. But when I flew the anti-submarine, most of our flights were at 1,000 feet, or 300 meters. After a 12-hour flight, we had to wash the airplane down because it was coated with salt, just at 300 meters above the oceans. But anyway, we knew that there was more cloud than there were condensation nuclei.
A new phenomenon is now on the top priority research at NASA Space Meteorology, and they are the intensification of cosmic rays. They began to show up since December 2014, and I was receiving emails regularly where they showed new data and warnings. First, the warnings were only for astronauts working too many days in space. Then were for the high-altitude airplane pilots because they are exposed many hours and in repeated flights. Then warnings were also issued for passengers and then for the alpinists climbing very high mountains. Can you see this pattern? And I have here a full graphic result.
Yes, well, it's another one of those things where the cosmic rays have always been there. It's just now that somebody in government has decided that they're a problem, and therefore they're putting out these stories of, oh, the level's going up and we need to be worried about it. What did we do before we knew this information? Now, what's interesting from a scientific point of view is the protective devices that we have against harmful radiation, particularly from the sun. Now, cosmic rays, of course, can also come from deep space. They're not just from the sun. And in fact, the amount we receive is controlled by the magnetic field of the sun. But one of the things that you're going to see going forward is that the Earth's magnetic field protects us from a lot of this cosmic radiation, okay? The Earth's magnetic field has been weakening for about 1,000 years now. We measured it in the Swiss mathematician Gauss was the first to measure the strength of the magnetic field. So it's measured in Gaussian units. It's been decreasing for about 1,000 years. Some people think that we are heading for a complete disappearance of the Earth's magnetic field.
Oh, yes, now I remember. It didn't cross my mind, but I also wrote into my book about the Earth's magnetic field changes, and I remember I made an interview with one of the leading top specialists in this domain.
The reason I'm raising it is, of course, because...
Gary Glesmeyer.
Yes, yeah, okay. The reason I'm raising it is, of course, because what was the impact the last time? And of course, it's related to a magnetic reversal. So what happens is the Earth's magnetic field collapses in to zero and then builds up again, but with a reverse polarity, so that the North Pole are reversed. And you can plot those in layers of lava because there's rocks that are very sensitive to the Earth's magnetic field, and they align themselves with the magnetite, for example, is one. And it aligns itself with the Earth's magnetic field at the point at which it cools below a certain temperature. That temperature is called the Curie point, after Madame Curie, who was one of the great scientists of all time, one of the few to get 2 Nobel Prizes. And she noticed that at a certain temperature, those things align. So they were like a tape recorder locking in what the magnetic field was at the time they were formed. And as you go down through the layers of lava, you see, and this is part of how they prove continental drift, that the continents were moving. You get normal, which is what we have now, North Pole, South Pole, and then you get the next layer, and it's the reverse. And you can, it changes surprisingly rapidly, the magnetic field collapsing. You have what they call epochs. That is a period of about 1 million years or so where it's predominantly normal, as we are now, and then predominantly reverse. But within an epoch, you can have an event where in a very short time period, 10,000 years or so, it reverses itself. And of course, they don't even know what causes that. Part of the problem is that what creates the Earth's magnetism? A lot of people think it's because of the Earth spinning, but if that's what's causing it, then to have a reversal, the Earth's got to stop spinning in one direction and start spinning in the opposite direction. There's no evidence of that. The current belief is that the Earth is made up of 3 different spheres: the solid inner core, the liquid outer core, the mantle, and the crust. The crust is actually very thin. Each of those, because of their different densities, is spinning at a different speed. Each of them is creating a magnetic field that at one point complement each other to create one polarity, and then as they spin at different speeds, they cancel each other out, and then a new magnetic field is created. That's generally what they believe is happening now. The interesting thing for me is the relationship to its impact, because there is evidence that when the magnetic field has gone to zero, there have been mass extinction of species on the planet, particularly soft-bodied creatures, shallow water creatures. And it's also very clear that the radiation that's allowed, because the magnetic field is not there, impacts DNA within our organic structures. So they think a lot of mutations of genes and evolution are related to that impact of the harmful rays on the DNA. Now, it's interesting because, of course, one of the reversals, most recent ones, it was 800,000 years ago, is called the Olduvai reversal. Now, Olduvai is the gorge in Africa where they found early humans. And obviously those humans lived through that magnetic reversal. But the question is, did it have any effect upon their DNA and therefore the pattern of evolution that occurred? Those are the things that really fascinate me about it. But in terms of the weather and climate, the cosmic rays, of course, we now know that as they penetrate through the atmosphere, in the lower atmosphere, they become condensation nuclei. And so the amount of low cloud cover varies as the amount of cosmic radiation varies in the lower atmosphere. And that, of course, creates cooler temperatures. Because we'd known for a long time, and we did talk about this before, that as the sunspot numbers varied, the global temperature varied. But the danger in science is just because you have a correlation, you cannot assume that there's a cause and effect. It's like I talked earlier about saying, oh, well, the front bumper's moving there, and then the bump bumpers. I'll assume that there's a cause and effect between them. You can't do that. But in 1991, a couple of Swedish scientists started looking at the pattern of changing sunspots related to the solar magnetism. And in about 1998, 2000, Svensmark came out with the cosmic theory, which shows that as the sun's magnetic field strength varies, that's manifest or seen on the surface with changing sunspot numbers, but it affects the amount of cosmic radiation that reaches the Earth. So that the sunspots are not causing the cloud cover, but they're simply reflecting that this change is going on. So the cosmic theory is now pretty well accepted and shown. And of course, the cloud cover or clouds are very difficult to put into their computer models. And the reason for that is the lack of surface data. We talked earlier about the lack of weather stations, but also the size of the squares that they divide the Earth's surface up into. About 3 degrees by 3 degrees. Well, you can have a complete cloud thunderstorm system, and it doesn't even show up at that grid scale. So it's very much like, as you know, TV and computers, the quality of the picture has improved because of the number of pixels or dots that you have. Well, when the computer models are like, you know, very, very crude picture, because the size of the grid that they can handle doesn't include major weather mechanisms such as these thunderstorms. So when I talked earlier about the Hadley cells, there's on average 10,000 thunderstorms on the Earth at any given time. The computer model can't handle those. They can't put those into the computer model. So as Roy Spencer, one of the best climate scientists, said, computer models don't do clouds very well. And until you can include the clouds in the computer model, you're never ever going to be able to accurately make forecasts or understand what's going on in the weather. Clouds are a very important part of it.
Only 2 minutes remain, and I have a final question. I always had a problem with getting colder and winters. How long do you think we have until very cold temperature we will be expecting in Romania?
2 or 3 years, you're starting to see the cooling continue. But as I said, don't forget, I said you're going to also have very warm spells. So the variability, the range of temperatures will keep increasing, but it will be primarily because of the winter cold. One of the things that's happened over the last 30 years or so is the winters have got warmer. The summer temperatures have remained essentially the same. That's now reversing. The winters are getting colder, and it will continue. So you're already in progress for it. So you're going to see some very, very cold outbreaks of Arctic air from Siberia. It's certainly going to intensify in the next 2 or 3 years.
Dear Professor Tim Ball, I thank you greatly for participating to our Science and Knowledge TV program. And let's keep in touch for the next years as the climate phenomena intensifies. And I wish you best. And you may share our interviews on your web pages and blogs.
I haven't put it up there yet. I must do that. I don't handle my own blog. I've been telling people about it, and I've been circulating it through all the internet sites. And I made reference to your website. I hope they contact you about it, because I think what you're doing is extremely valuable. But there is so much to study, and one of the things, of course, is to stop the government panicking us into things that we don't need to be worried about. There's enough to worry about without that.
I thank you a lot for participating to our program.
Yeah. Thank you, Christian.
Let's meet you again next year for a new interview.
Okay, thank you, Christian. Have a good summer.
Goodbye and all the best. Știința mediului nu este și nu va fi niciodată o știință exactă, însă cele mai plauzibile prezumții pot fi realizate dacă oamenii de știință colaborează în mod constructiv și non-politic. În lipsa acestei colaborări, în loc să înțelegem cum funcționează clima, de fapt vom ajunge să elaborăm sisteme de credințe false în tabere contrare care luptă pentru a-și impune propriile dogme. Unele dintre ele ne spun că e vorba de o încălzire determinată exclusiv de activitatea omului. Altele ne spun că există încălzire, dar e de origine naturală. Altele ne spun că vine o răcire. Rămâne de văzut. Doar trecerea timpului ne va releva adevărul, confirmând sau infirmând cele prezentate de către profesorul Tim Ball. Fiți alături de noi data viitoare la o nouă întâlnire cu Știință și Cunoaștere.